the recording. You could go ahead and do it, Dan, and let me know. Okay, allow recording. So we are good. All right, so ladies and gentlemen, welcome back to the Henry George School, and we apologize for the technical difficulties that we had. And Michael is connecting from Ireland. It's a little bit challenging when you have to run an event with participants on the other side of the world, but I'm glad we could make it tonight. So this, as described in the website, this is a three-part series that is focused on decarbonizing the economy, the challenges and prospects. So we will have three different lectures and three different lecturers. And tonight being session one, we have the pleasure of welcoming Professor Michael Morris. Michael is a professor at Trinity College in Dublin, and is also the director of EMBER, I hope my pronunciation is correct, the Center for Advanced Materials and Bioengineering Research. So Michael will speak tonight about his research on the need to achieve decarbonization milestones and the cost associated with such a transition. You may notice that Dan Sullivan also is here. Dan is gonna give us a brief intro to what his talk next week is gonna be about. Mari is unfortunately not with us tonight because he's flying back from Seattle, but I'm hoping he could make it so that he could say something about his talk. So the last session, which is gonna be 3 weeks from now, is gonna be a little bit long because we are planning to have all three speakers to be there to answer some of the questions. Without any further ado, I'm gonna just let Michael step in. Michael, the floor is yours. Thank you.
So first of all, I'll share my screen and hopefully everyone can see that, and I hope that page is up and down okay. So just to give you this is kind of aimed to give you a broad overview of things that I guess we need to think about really in decarbonizing the chemical and materials area, which is quite different, I think, and quite a different challenge, and an even more challenging prospect than the decarbonization of energy. And I'll try to explain why, offer some kind of idea and perspective about whether that's achievable, and how it might be achieved, and some of the technologies and some of the approaches that are being talked about in the literature. So I'm not a climate scientist, first of all, and I don't pretend to be. I'm very much a material scientist and looking at how we use materials, and in my case, particularly in the polymer space. And I've shown some pictures on the top right about really what I do is I'm actually a nanochemist, so I don't use very much materials, nanogram type quantities in a single experiment, where I try to make what look like either very ordered structures or disordered structures from polymers, and those polymers largely investigate how we might make new transistor devices from them. So I'm not going to talk about that, but that is my background. But in the last few years, I've really had to think about plastics like many other people do in terms of the damage that they do, where we source the materials from, the use of things like forever chemicals, which are made from polymers, and the way that we're changing the regulation, which really limits how we use that, and then some of the concepts about how we might make polymers more recyclable, more sustainable. So that's kind of how I've gone. I work very closely with the ISO standards organization in developing standards both for measuring the sustainability of materials in terms of things like circularity, how we measure and assess how circular something is, and also how we might make standards which force people down the line of looking at the sustainability of materials as we use them. But in this particular talk, I'm really going to talk about the origin of our reliance on fossil fuels, the effects that they've had on the environment and biodiversity and climate change. So I think we know this, but I don't know necessarily whether we all understand the implications of what's likely to happen if we just ignore the carbon controversy. Really looking at the petrochemical industry, not in the immediate term, not in terms of moving towards goals and climate goals for 2030, but more in the 2030 to 2050 space. And there is a very significant problem that we have is defossilizing energy. I won't say it's simple, but we have technologies and they're becoming off-the-shelf technologies. They might be expensive, they might precipitate economic changes, but they are possible to do that. And given enough money and enough will, I think we can solve the decarbonization of energy. What are the challenges in terms of going beyond that scope towards defossilizing completely by kind of 2050? What the objectives and impacts are, and a perspective really on what's going to be needed in terms of the way that we live our lives as a society and the environmental and economic systems. So that's a kind of overview of what I'm going to try and talk about. And before I start, I'm going to talk a lot about figures. We really have to approach the answers to these problems in a very holistic or systems thinking way, where we analyze the whole system and take as much data as we can to kind of predict what are the best and most impactful decisions that we make. So that systems thinking means that we need excellent data. And we don't have excellent data. And that's because it's difficult to analyze. So if we have to think about how do we estimate the emissions from cars, well, we can get that data fairly accurately. We know how many cars in the world, we know the average size of an engine, we know the average efficiency of the engine, and we can sum that up and we can get a reasonable estimate for, say, CO2 emissions. But when we get into industry, we start having to do guesswork because many industries don't know how much CO2 we produce. And I've just chosen the example of the uncertainty in this data. And this is an article taken from 4 or 5 years ago from the Guardian newspaper in the United Kingdom, which was one of the first papers to break this story that the semiconductor industry, which we think of as being very clean, very, very efficient, might have a dirty environmental secret that very few people know about. And to all intents and purposes, it's shown on the right, the chemical industry is hugely successful. It's changed all our lives in a very positive way. Our ICT, our communications, the use of new car technologies, driverless cars, from ordering things from Amazon, everything we do is mediated through these little silicon chips. And that industry has grown and grown to the point that it cannot meet the demand for silicon chips. We make, right? So, and this is the issue, it's that there's some figures there for greenhouse gas emissions in millions of tons. So that sounds like an awful lot, but probably that data is underestimated. So 2023, we're likely to make somewhere between 1.3 and 1.4 trillion chips, right? And they're tiny things. A large silicon chip will weigh 3 or 4 grams, a small chip, 1 gram. But for every gram of a silicon chip, our most likely estimate is that the emissions associated with that is 4 or 5 kilo of carbon dioxide per gram. Multiply that by trillions of chips. you can see that the emissions associated with the silicon chip industry are probably 4 or 5 times the estimates that are published, and probably account currently for 10% of all emissions. And you can probably look at every industry, every sector of industry, and kind of realize that that side, the emissions due to industry, are very difficult to quantify and probably underestimated. So that's just kind of one example of the size of the problem. And the size of the problem is we don't even know the size of the problem. So trying to make decisions without having real hard data is very difficult. And clearly one of the trends we have to be is producing standards, producing regulation and policies at government level, which force companies to actually reveal and calculate and estimate their emissions in a very quantitative and rigorous way. So that's kind of the first problem that we're going to say, and we're going to talk about data, but lots of that data is it's not maybe not controversial, but there are questions about its validity at every level. Why this matters? So everyone knows that there's a climate problem, and it's largely a modern problem. On the top graph, we can see that carbon emissions have generally just carried on increasing. Kind of hopeful at the moment that we're plateauing. There was an obvious dip around 2020, 21 due to COVID-19. But they've increased incredibly. Then the bottom graph shows the actual amount of carbon dioxide in the atmosphere as a function of time, and you can see in the 1950s we had an average level of about 300 ppm. If we look at the kind of the near history, 800,000, 700,000, 500,000 years ago, we're far above, even at the 1950 level, we're far above the average mean CO2, about 200. And we're currently at about 425 ppm of carbon dioxide, which is the highest it's ever been in modern time. So the link between global warming and CO2 is absolutely a rigorous demonstration now. The reason that's so frightening is that since the formation of the world, there's been some catastrophic events linked to high CO2 levels. The most important of which was back about 250 million years ago, which is essentially the end of the Carboniferous period of history, where because of volcanic activity, a strong area of volcanic activity on the single landmass that was present at the time, CO2 levels probably rose to somewhere between 1,200 and about 1,700 parts per million. So 3 or 4 times the current level. But that took 40,000 years to increase from a baseline level of 200 ppm to about 1,400, 1,500 ppm. We've gone from 200 ppm in 2 generations. And so that's a trigger point. We know we have to limit global warming associated with this to around the nominal 1.5 degrees. And it should be said in the Jurassic period, or the end of the Triassic period, carbon dioxide led to a warming of the global temperature by 10 degrees. But that 10 degrees triggered the greatest mass extinction we've ever seen on the planet, and wiped out over 90% of all life on the planet. So it is linked to catastrophic events. It set back evolution, that single burst of CO2, if we like to think of it like that, set back evolution by about 150 million years. and took about 30 million years to recover life on the planet back to its original density. So this CO2 problem, it isn't imaginary. It's not being exaggerated. There's very significant climate issues associated with that. But it's worth looking, I think, at why we've built this reliance on fossil fuel, and it's the fossil fuel burning and use which has driven these CO2 levels. Why we've built up this reliance. And the obvious trigger point, and obviously point in time when everything changed, was back at the start of the Industrial Revolution, which is often pinpointed as one person. Clearly wasn't one person that did it, but it was John Kay, an English wool merchant, who'd gone to France and seen the operation of a flying shuttle, which sounds like a very complicated thing. It wasn't. It was just a little guinea on wheels that weavers could throw across the weave from one weaver to the next. And as the weaves went this way, the guinea went this way, and you could actually throw this across and speed up the manufacturing process of fabric. But not only speed it up, you could scale it because you can throw things further than you could pass them. So that became a trigger point. Then we know that the fabric industry then led to the dye industry, which led to the chemical industry. We then saw the transport of chemicals, transport of goods and materials, using first of all canals and then trains, and we see this escalation. And all of them have necessitated the use of an energy source, and the easiest energy source we've had has always been fossil fuels, be that coal, natural gas, or oil. So while we see that as the cause of our current problems, it is also the cause of societal advancements across the globe. So if we look at life expectancy through the start of the Industrial Revolution right through to the present time, that has continued to rise. It's more than doubled in the last 500 years. The only dip in that is that some countries did see a dip during COVID because of the deaths, but that has continued to and is expected to continue to rise. Because of that, because of the industrialization of food production, we've also seen us able to feed more and more people. So not only have we seen life expectancy increase, we've seen huge population growth. And we think the population growth is probably going to plateau at about 9 or 10 million. But those figures are far from certain. And we have yet to see whether population growth globally is going to stabilize around that figure. Importantly, because of the Industrial Revolution, the availability of materials, the industrialization process, generation of circular money where we pay people to do jobs, they do more jobs, to get paid more people are employed. We see this expansion. We've seen huge decreases about the numbers of people in poverty. And that's all been triggered by essentially the oil fossil fuel industry. So the oil industry, of course, is still central to this. It's about 7% of the world's economy. Our demand for oil is growing, it's not declining. Even though we're using more and more renewable energy, the growth of population, our demand for more goods, increase of lifestyle, etc., still leading to greater demand for the use of fossil fuels. And the oil industry is obviously, 4.2 billion tons per annum, or 100 million barrels a day. That's kind of the amount of oil we extract out the ground. So it's come at a huge cost, but it's produced enormous societal value. And that societal value is mediated around mass production and mass consumerism through industrial efficiencies. But it has led to environmental disaster. So the increase in population, the increase in lifetime, the decrease in poverty, the need to drive agriculture to an industrialized process, that's all led to tremendous climate changes. I'm currently 1 degree hotter than we were 50 or 60 years ago. The central figure there is there are loss of wild land has been absolutely incredible. So I think there's a figure often quoted that since the 1930s, so before the Second World War, that we've lost between 50 and 60% of wild space. And that's because we've changed that wild space, that forest space, into grassland, crops, and grazing. So we're now at maybe 20%, 30% of the Earth surface, of the habitable land surface can now be described as wild. And that's obviously been linked to massive changes in biodiversity. And for the first time ever in human history, we're seeing changes, an important change, a decrease in the biodiversity on the planet. So if we're going to blame fossil fuel, it's worth kind of analysing exactly what we do with that fossil fuel. If we look at crude oil, nearly half of the gasoline that we produce is used for cars. About 22% is used for heating our homes. We then have other products, which are the chemicals, polymers, the acids, and all the materials that we use for our modern industry. 10% for flying, 4% for propane, for outside heating, etc., and 3% goes into asphalt. So that's the kind of breakdown that we have. Natural gas, also used for energy, of course, mostly electric power, about 24%. And then we have vehicle fuels, pipeline fuels, various industry operations, and then domestic and residential heating. So we can see this pattern that roughly 66% of all fossil fuel is used for auto transport and energy. And that's a bit of the problem, which is easy to solve, whether that's by turbines, hydropower, ground heating, wherever the renewable energy sources are, solar panels, they all fit into fixing that. It might cost a lot of money, but it's fixable. The other bit isn't fixable at the moment. So around 10% of oil is used for cement manufacture. Around 1.5 of all coal is used for making steel. Around 15 to 18% of oil and gas is used for chemicals and plastics, and break that down in a little bit. The rest is asphalt, propane, and kerosene, so roads, aircraft fuels, and we don't have technologies at the moment to replace that. If we look on the right-hand side of this slide, we can see what we use oil for, which might well surprise people. About 3% of all petroleum is used to make the medicines that keep us healthy and well, or 132 million tons. The plastic industry is a huge consumer of fossil fuels, around 0.9 billion tons of oil and gas. And the plastics industry, every piece of plastic, 99% of that comes from fossil fuel sources. Around 0.9 billion tons of oil and gas is used in the construction industry. That's steel, cement, plastics, coatings, etc. And we can reliably add the semiconductor industry, growing incredibly quickly, as another 100 million tons. And one of the dirty industries, or one of the industries might guess in terms of fossil fuel, is car manufacturing, which actually is a relatively small contribution to what we use oil in. But if we take all those figures, if we're really going to defossilize industry in terms of the carbon, right? So think about the energy, right? Let's assume that we can solve the energy side, but just the carbon materials we need to make things like methanol, ethanol, polymers, all those carbon-containing substances, we probably need 1.5 billion tons of carbon. And just for polymer production, we probably need 1 billion tons by 2075. It's 1 billion tons of carbon that we currently source from fossil fuels. So that's a real difficult problem for us to square. And that's really what I want to talk about. And I like this slide from an OECD report, which I think sets a juxtaposition between what we're told about plastics and what is the actual truth. And I love some of the figures that are in here. And it kind of frames the challenge, because this is a projection of what's going to happen in the plastics industry between now and 2060. So currently we make around 500 million tons of plastic per year. And those 500 million tons all come from fossil fuels. By 2060, that will be over 1 billion tons. But the top left has primary, so that's the stuff we dig out the ground. Secondary is recycled plastic. And it's important to realize that despite what we think about recycling in any form, it's a small contribution, and it's going to remain a small contribution. So it's not the savior isn't going to be the constant recycling of plastics, because that's technically impossible. It's going to be to find where we can make these from, how we can find the carbon to make polymers that isn't from traditional fossil fuel sources. These are the goals set by the IPCC to limit us to this 1.5 degrees centigrade. And the goal is around 2050 to get to net zero carbon dioxide. So not net zero in terms of all greenhouse gases. Talk a little bit what those greenhouse gases are, but we have to get to net zero. And that's to limit us to 1.5 degrees centigrade. Now, most people are saying that the 2050 target is going to be missed, and that a more realistic target is 2 degrees, which will require us to get to net zero somewhere between 2070 and 2080. So it's an incredibly demanding schedule to get to 1.5 degrees centigrade. And we really have to think about whether that's possible. Now, even when we look about that, it's that if we're going to get to 1.5 and net zero, it's worth thinking about where we're heading. And this, the slide on the bottom left, the picture on the bottom left, really explains this in terms of what we're extracting out the ground. So this is all the minerals, oil, etc., that we're doing. There is no hint of that extraction rate, which suggests that we will get anywhere near our 2050 goals, because our material extraction rates are increasing. And it's not projected to stop within the 2050 or even the 27 period of time. So while we might set ambitious goals for renewable energy, the goals for actual net zero are incredibly taxing. Some key things that industry have to do if we're going to meet net zero, whether that's 2050 or 27, halving emissions by 2030 seems to be a must, but that seems very unlikely. The net zero goals means that industry must limit its emissions to 90% of what they are now. And the remaining, the 10% that we're going to aim for, that has to be taken out by other techniques such as carbon dioxide trapping or direct air conversion, where we trap CO2 out the atmosphere. So that's not seen as a potential solution. We really have to cut emissions in industry by 90%. So these are incredibly exhaustive goals. But the bottom line is, to do that, we have to defossilize chemical production and industrial production of all materials. And that means we need to find 2 billion tons of renewable or net zero carbon by 2050. And that's 2 billion tons of carbon that we don't have at the moment from renewable resources. So it's just something we don't have, and we're not really thinking about at the moment very much at all. So where does the carbon come from? And I think if we're going to think about this, going to do a systems think about it, this is the information that we should really consider. The fossil fuel is not available for use. Now, that might not be true. If we can find clean ways to turn oil to chemicals, we should think about what those clean means are, because there's lots of petrol, there's lots of oil in the ground, there's at least 1,000 years supply. And maybe we look at what we've got available at the moment in terms of delivering net zero technologies rather than looking at alternatives. So that's a bit of a controversial thought, but it's something we should be thinking about. We currently emit 40 gigatons just from the technosphere of CO2. That's 50 of emissions, 55 gigatons if we think about CO2 equivalents, so that's all the methane. So 40 gigatons of CO2. Give you an idea of how big a gigaton is, because this is something that does it. A gigaton is the mass of all the land mammals on the world other than humans. And it's twice the mass of all the humans on the planet. So that's how much CO2 we're emitting. I mean, the phenomenal amounts. Offsets will not work. Just planting trees won't work, because even at the current levels of emissions, we need about an area at about 5 times that of the Amazon rainforest if we're just going to use trees to capture the CO2. So that's not possible in a realistic term. We have to assume that there's a shortage of land and food, and we need to decrease land use, not increase it. So part of the problem is we don't have enough land, we don't have enough trees, we don't have enough wetland, and we've dried it all out. We have huge industrial plants taking up space. We have an increasing population. So we can't just assume that we can develop solar panels across the rest of the space that's available to us. We have to think about, at a minimum, increasing the free space on the Earth by 5% every 4 or 5 years to reverse some of the trends that we see. We can only feed ourselves because of the production of fertilizer, which increases the global crop yield by somewhere between 2.5 to 3. And fertilizer is essentially ammonia, which is nitrogen plus hydrogen. So that hydrogen has to come from somewhere. And at the moment, 300 million tons of fossil fuel is used to make fertilizer. So any technologies that we have will rely on us finding hydrogen from somewhere else other than fossil fuels. And that's another difficult. We can't use plant crops for chemicals, so we can't turn oil plants into chemicals, because we need them to feed our growing population. Renewable energy is a prerequisite. And we'll have to assume, in any kind of reasonable estimate, that it's kind of limitless after 2030. Now, that's probably not a meaningful guiding principle, but we have to assume we'll meet the 2030 goals. Even though meeting those 2030 goals, the best estimate is for that is going to cost us around $300 trillion. And also we should think that the IEA suggests that in 2022, the amount of renewable energy we have was 5.5%. So that gives you, right? So we're another 6 years to meet these 2030 goals in energy. So we're unlikely to meet them. We haven't got the spend rate, and we haven't got the government will to increase the spend rate to meet those demands. But we have to assume that that's what we're going to do. Right-hand side, it just shows where these emissions come from. As about 66% of them, following the oil trends, comes out of fossil fuels. Some carbon dioxide from forestry, so that's burning of forests, plant lands, etc. Methane from largely from crops and animal feeds. Nitrous oxide is an important a byproduct. It's a big greenhouse gas in terms of its effect, and that's largely by the burning of fossil fuels as well. And then we have these fluorine chemicals, which are largely due to some of the processes of the semiconductor industry, which can be 1,000 times more dangerous to the atmosphere than carbon dioxide. So yes, if we take fossil fuels out, it'll get us part of the way, but it's not going to get us anywhere near the full way. So we have to do something. And one of the background figures that we have to think is that land is extremely scarce. And this is an IMF report showing where we might get land from outside Western Europe, where we're fairly well planted out. We have a nice balance of the trees. With certainly in Europe, we don't have much free space for us to do anything more with. So Africa and South America are obviously the wildest places that we can think of in terms of growing it. And the upper thing, the red bit, shows the value of land, and there is a land race to buy this land. So you can see these very select areas decreasing in price as we go from yellow through to green. And you can see the green, for instance, on the Africa figure, is really around the Sahara Desert, because that land is cheap, but useless, very poor returns. But the really sought after land is in hotspots, which, if you look at it, agree almost exactly with where the Amazon rainforest is and where the Great Plains are in Africa. So they're really wild spaces that we need to preserve. But they're also the parts of the world where we can target things like crop growth. So we have this terrible juxtaposition that we need more lands for crops to feed people, and the only land we've got is exceptionally value in terms of biodiversity and forestry. So incredible challenge for us to think about how we might feed the world while increasing or decreasing our reliance on fossil fuel. Some simple chemistry before we start looking at solutions, which are kind of important. The fossil fuels, I've left coal out of this. It's a dirty fuel, and most people are trying to stay away from it. But if we look at petroleum and natural gas, they're very rich carbon sources and very rich hydrogen sources. So when we make chemicals, when we make polymers, we need hydrogen as well as carbon. When we start going to wood and other forms of biomass, they're low in hydrogen, and we do need that hydrogen to come from somewhere as well. By the time we get to carbon dioxide, it has no hydrogen in it at all and no oxidative power. So it's fairly useless unless we're going to put an awful lot of energy into it to make it into things which is useful. The oil process is reformed. Right, so we raise its hydrogen value, its value by making more double bonds, and it's cracked to give us chemicals in huge supply and very easily produced and very densely produced. Our methane, we make it via the cracking of oil, or we just collect natural gas to do it, and we make chemicals via syngas process. If we're going to use wood, we can make that into wood by tinning it, by just burning it to make carbon dioxide. And then if we've got a hydrogen source, we can hydrogenate it to start making chemicals. We can also do pyrolysis, which is kind of underused technique where we just, pyrolysis is posh word, a word for when we bake in the absence of oxygen, which we do every time we make roast beef of a Sunday or a roast joint. We put it in an oven, there's an oxygen deficiency, and we generate fat and oil from the beef, and that's a pyrolysis process. So we can make valuable bio-oils, other bioprocesses, where essentially we can react it with enzymes and things which break it down into other chemicals, but very unproven technologies if we're going to use wood to do it. Carbon dioxide, as I said, it's fully oxygenated, so there's no energy value out of carbon dioxide that we can obtain. And the only way we can break it down is to react it with other things, obviously hydrogen. And there's a little diagram there showing if we've got lots of free hydrogen, which if we've got excess renewable energy, we can hydrolyze water and generate the hydrogen to react with the CO2 to give us the things that we want. Methanol, ethanol, propanol, ethane, and all the precursors to the very valuable things. But we do need this enormous hydrogen amount, which needs a kind of an excess, if you like, of renewable energy. The other technologies that we've got are often called carbon capture, but there's essentially two forms of carbon capture. Is where does a lot of carbon dioxide in the atmosphere come from? Well, it comes from combustion, so burning of all fossil fuels generates carbon dioxide. That's where we get the energy. It comes from cement plants, and it comes from iron manufacture. They're the big sources. But if we think about those, we think about a combustion plant, CO2 is coming out of the top of a chimney. And all we need to do, it's still a very expensive technology at the moment. We can capture that carbon dioxide because it's flown out of a pipe. We can compress it, and that's how we separate it. We can put it in the tank, and we can try and use that carbon dioxide, or we can store it by injecting it into oil wells. Those processes are available. And in fact, when you look at the carbon footprint, is if we could get carbon capture right, actually burning fossil fuel in a very highly efficient turbine, plus carbon dioxide capture and disposal, safe disposal by injection into bedrock, you probably get down to a carbon footprint not far off that you get from wind turbines. And that might well become a technology which becomes ever more important if we can't meet our energy goals, our renewable energy goals, by some of them are of things like wind turbines, solar panels, etc. So that's carbon capture, and it can take an awful lot of the carbon that's associated with things like cement and iron manufacture, if we can afford to add those technologies. But there is a cost. For carbon capture, as you can see, we need to compress the gas. We need the downstream technology to put it into trucks and then inject it. So it kind of does add costs onto our products. And at a time when construction industry is under great pressure, but it certainly is in Europe, because of the cost and the energy footprint and growing population, etc., it would probably double or treble the cost of a bag of cement to implement those carbon-saving technologies. And at 10% of the world's economy is construction, that price rise is probably unsustainable. And that's one of the challenges that we always have, is the economic challenge rather than the technological challenge, which probably can be implemented. The other thing that people talk about is the way of solving the problem is to look at direct air capture. So this is, as it sounds, is you pass air through some sort of system, you capture the CO2, and then you can either use it by reaction with hydrogen to make things, or we put it back in the ground and hide it again. But it's very high technology. It costs, so you need special materials to capture the carbon dioxide and concentrate it. You then have to heat up those materials to release the CO2, and then you get all the pressure that's associated with it. And each of them come with a big carbon footprint. And the top right-hand figure kind of shows that if we're going to absorb a large amounts of CO2, once we get to significant, meaningful amounts, we probably need as much energy in the direct air capture as we use for the whole of the globe anyway. So enormous energy costs. Now, if that energy is very freely available, it doesn't make any difference. But at the moment, we simply cannot afford, on energy terms alone, to have large direct air capture works. This is the biggest direct air capture plant in the world. It's in Iceland, and it captures about 4,000 tons per annum of CO2. That's probably scalable, even within that plant, to maybe 4 or 5 times that. But at the current size, even if we look at the emissions from Ireland, which is about 5 million people, we'd probably need 15,000 of these plants to give us net zero, at a cost of somewhere between $300 to $600 billion. So we know the technology will improve and those costs will come down. But again, at the moment, we can't think about this being a way of offsetting or solving the CO2 problem. So we have to find something which is going to just defossilize us. Defossilization is the only solution. I won't really talk about this technology because I think I've talked enough about the CO2 hydrogen problem. So if CO2 capture isn't a problem, isn't really a solution or a source of carbon, what are we going to do? Well, let's think of wood-based biomass. So trees are the best form of biomass, largely because, if for no other reason, they grow vertically. So yes, there's other forms of biomass, whether that be crops, low-value crops, bushes, seaweed, but they all take up huge areas. Forests do not take up huge amounts of area. Forests are obviously sequester. They sequester about 11 to 20 tons of carbon dioxide per acre. That depends on the type of tree, its maturity, etc. Deforestation, so whether that's the Amazon or parts of Europe, parts of North America, but deforestation is probably responsible for 10% of global warming. So clearly, afforestation is a really good technology. And we can harvest around 2.2 billion tons of roundwood. If we assume 1 ton of wood is equal to about half a ton of carbon, the rest being oxygen and hydrogen, we can start to think about how much wood we want to source our 1 to 2 billion tons of carbon. Now, even thinning, as we grow a forest, to keep that forest in good health and manage the forest, just the thinning process where we decrease the number of trees per unit area. We take various bits of the trees off in terms of the branches to make them more efficient in growth. We can harvest about 15 tons of carbon per acre on a continual basis, right? So every piece of land, 15 tons per annum. So if we think about what we need, our 2 billion tons target of carbon, that's only about 530 million meters squared. It's less than 1% of the Earth's surface. So wood as a potential source of carbon other than biomass is a pretty good bet. It takes up quite a small amount of surface. We know how to manage trees. We've been doing it for a very long time. And we can do it sustainably. In the sense that we regenerate the land, we recover the land. The problem is that we don't have that much time. So this might be a technology for 50 to 70 years ahead of now, but it's not going to meet the original deadline. But if we're really going to start an afforestation program aimed at defossilization, the chemical industry and materials industries, we really have to start that as soon as we want. We nearly have to think there's also that biodiversity. So we have to think about natural forestry, our locally grown trees. We shouldn't be relying on monocultures because we know that's negative in terms of its effect on the land and biodiversity. And then we should also think about converting it to chemicals. Currently, biodiesel from wood is a really large market, and it's growing. So we do have the technologies there to convert wood into valuable chemicals, but we really have to make the commitment to actually seeing it as a solution to defossilization, as well as just a form of biodiesel. So I'm going to close and make some final comments, which I guess are conclusions that you probably draw from some of the things that I'd say that I've just said. Business as usual is not possible. Our problem is that we've industrialized a lot of processes which have had a detrimental effect. And that has largely been in terms of carbon demand. But if we're not going to use fossil fuel, we need a whole different industry sector, and we need a whole form of planning. And I'll maybe give you a degree of change. That does, if you look at a natural gas turbine plant, you can service a population density, a town of about 100,000 to 150,000 people on a gas supply plus a few acres of land, right? So that's what you need. Turbines are incredibly efficient, low land use. If you're going to do it from wind turbines, right, you need thousands of acres of wind turbines to generate that same effect. So there is a problem that when we change technologies, we also have to think about how those technologies are going to be intensified so that we continue to minimize land use, not maximize land use. The sources of carbon that we might have are really an unaddressed issue. There isn't an awful lot. There's research going on, but I think this general problem of where do we meet the next generation's carbon demand from, I don't think is being thought about in enough detail or well enough. We do have technologies. We still need new and improved technologies. And of course, I'm not mitigating the myriad of contributory solutions that might have. I mean, one of the things that we really need to think about is the circular economy. I spoke about the fact that we use 1 trillion semiconductor chips. Not one silicon chip is recycled at the moment. there's probably very little value of it, because once you've made it, it's actually assumed all the carbon, nearly all the carbon it's ever gone to. But we don't recycle that at all. So we have to think about things like the circular economy, where we recycle things, we reuse things. My personal view, as it's shown at the bottom, is that if we want to consume less resources, we need to make fewer things. That's the bottom line. Is recycling, reusing, all sound very nice, but they're expensive, they can be carbon intensive. If we want a half material use in the world, we just make everything last twice as long as it's lasting at the moment. But of course, the economic challenge of that to companies whose profits are mitigated around sales is nobody's going to produce technologies which reduce sales. So that's kind of a real challenge. We also have to think about the fact that all of these issues, the environment, the economic considerations, and the social elements is equal barriers to the technology. We have to do things which are going to free up land, and very often we don't take that land issue into account. We have to think whether society is ready for change. Is it ready for making their computers last 10 years rather than 3? Are we not going to change our mobile phones every 2.5 years? Are we going to drive cars which are 25 years old? Are we not going to remodel our kitchens every 5 years? The social barriers to this are incredibly changed. And of course, we're talking about changes in economic models. And with that, I guess I'll finish.
Thank you very much, Michael. This was a very, very brilliant presentation with lots of details, not only discussing the problems, but also outlining possible solutions. So I'm gonna just ask anyone who wanna ask a question to use the reaction button to raise their hands. We'll take a couple of questions. The session might take a little longer than we expected, but I think it's very interesting, so you may have a lot to say about it. Well, I don't see anybody raising their hand, so I have a question. I'm going to go ahead. Michael?
Yes, please do.
One of the solutions that you outlined after presenting the problem was managing sustainability. And you mentioned, for example, forest. And that kind of allowed me to connect it to what we've been hearing lately from organizations like the World Economic Forum, the folks at Davos. They've been pushing this idea of privatizing forests. So my question is, do you think that's the best way of doing it?
Do I think privatization of forestry? I think at the moment it's a necessary evil. But I think one of the problems with forestry, of course, is that if it's done on a private basis, someone has to make money at the end of it. And so for instance, we have lots of forests here which are based around a tree, actually a North American tree that we imported called the Sitka spruce. And we've developed forests for private gain, which are all Sitka spruce, and they acidify the lands. We get acidic runoff, which causes lots of problems. So we know that monocultures aren't a problem, are a very significant problem. So we have to look at how we diversify plantations in terms of natural crops, but very often they're crops that won't realize their full value. So a Sitka spruce will grow very quickly and we can have harvestable crop in 25 years. Now that's a long time to wait for a profit return, but oak is 70. So it can be done by privatization, but government has to set the regulation around that and also has to offer incentives for people to actually deliver it. So it's a very significant challenge about how you make that a profitable operation for people. So I think it can be done, but it needs an awful lot of thought and regulation.
Thank you. Joe.
Well, thank you for that outstanding presentation. It was terrific. I hope it's available to the general public at some time soon. It was just amazing. I have a couple questions. One is, well, I'll give you both questions at a time. You can choose who you want to answer. One is, do you see any hope for technological solutions where we somehow reflect more light? And two, is the enormous funding that you said is necessary, does that make it require monetary reform? That is, government produces money directly rather than relying on banks to finance this enormous spending, to reallocate resources the way you described is so necessary? Thank you.
Yeah, so on the first question, are the technical solutions? There are obviously technical solutions to some of these problems, but I don't necessarily know if we know the cost of those technical solutions, or even if we're thinking about the cost of the technical solutions. So one of the solutions that's clearly mooted is solar cells and solar panels for generating energy, and I think they offer a real solution in semi-rural and rural areas where we've got lots of land space, we have large roofs and low population densities. And one of the things that you always see mentioned about solar panels is that the sun is a limitless source and generates X amount of energy on the earth. But if you just take that and say, you take a very efficient solar cell, which probably 25% uses 25% of the energy that hits it, we still need to cover about half the surface of the Earth with solar cells to be energy neutral, which is clearly impractical. So it's a useful technology, but technology we should develop, but we have to think about how we balance that in terms of the fact that we have to think about the land that we use, making some of that land free land, open space, how we mitigate those things. So that's when there are technical solutions, but I don't think the solution is technology. We can't just swap out, and I don't think that's ever worked. We can't swap out a fossil fuel technology for a non-fossil fuel technology unless we understand exactly how that's going to affect things like biodiversity as well. So I think we have to be very wary about technical solutions. And I don't think we always are. We could be chasing these technical solutions for the next 100 years and literally doing that while Rome burns, if that's not a mixed analogy. So I think we have to be very careful. I think those solutions are available, but they cost a lot of money. Where that money is coming from, most of the hope is that it's private investment, so that, for instance, the oil companies switch their investment from mining for more oil into other renewables, and that's certainly happening. It's just not happening at a rate which is equivalent. So I think government has to fund this. I don't know where it gets the money from, but I think government kind of saying we want to do this, and this is what's got to be done, and expecting private industry to put in the capital investment. And it's 275 of capital investment, and I can't see that happening. I can't see that change in the way we structure and the way banks lend money to do that at the moment.
Thank you.
Joe, you have another question? Dan, do you have any comments to offer or any questions? I think you are muted.
Not a lot. It was very detailed. Next week I'm going to start from kind of first principles and challenge a lot of things that both the right and the left say.
Money.
Hello.
And
I'm going to talk more about the form of energy that nobody talks about, which is human energy, because that's the one form of energy that's wasted when it's not used. And going to talk about practical things that we are not doing because we are polarized, and the science is affected by ideology, and both the alarmists and the deniers are affected by ideology. And so a lot of things that make sense are not are kind of ignored because they don't resonate with either side. And that's kind of the Georgist experience in general with life, is that everything should either be private or socialized. And the idea that the free market either just works or just doesn't work is how the world is polarized generally. And the Georgist approach is just that the free market can work if we harmonize human law with what the classical liberals, especially the French physiocrats, called natural law. And but I don't know how much to get into that now, because I'll be talking about it next week. So,
any other comments or questions? Well, if not, we're gonna leave it there, and we hope Michael would be willing to share his slides, which I will, of course, be happy to distribute. And
Okay, yeah,
Dan is
no
gonna
problem.
be, okay, thank you. Dan is gonna be our next speaker. So Dan, do you wanna give us a little bit of a teaser for what's the session next week is gonna be? Next week, by the way, we are not having class because of Thanksgiving, but the week after.
oh, okay, good.
Yeah.
I was just looking at the calendar and saying, oh, I'm the day before Thanksgiving. No, it's okay. So it's the week after Thanksgiving.
The week after, exactly.
I don't, I think what I'm going to focus on, I'm going to touch on the science a little bit, and partly on how the alarmists have made predictions in the past that have been wrong, but partly on how those predictions actually might have been right. There were predictions of global cooling, and everybody ridicules the people who predicted global cooling. But it turns out that what they said about global cooling was that global cooling is being caused by all the particulates we're putting into the air. And we had a massive cleanup of particulates, such an extremely massive cleanup that that the global cooling never happened. Well, did we have that cleanup unnecessarily because the global cooling wasn't going to happen anyhow? Or were the people complaining about particulates right in that we rebounded from a kind of almost a 30-year trend of cooling? We quickly rebounded because we cleaned up all that particulate. And then now the global warming is leveling off. Could that be partly because China is generating tons of particulates? That China and India are not just emitting CO2, they're emitting particulates. So there are things like that. But I think we've beaten the science to death. The science, the alarmists have their science and the deniers have their science. And the economics of it almost suggests that it doesn't matter. The man who was once the most prominent environmentalist ever, guy's name was Reed Bryson. He was a total denier of global warming. But he said, but we should reduce our consumption of coal and oil anyhow, because we're not making it anymore. And it stores incredibly well. And there's just no reason to not conserve it, because once it's gone, there will be other problems. So there are lots of arguments that are not being made because they don't fit the polarization approach. And economically, there's intelligent ways to address this. So, and the players are not always what you think they are. The oil companies love cap and trade. The cap and trade will pay them to not suck up their oil as fast. And as you can see from what happened when Biden took office, and initially he reversed that, but initially he clamped down on everything. Oil company profits soared because the less you produce, the more you get for it. So there's those kinds of economic things. So I think I want to be very minimalistic about talking about the science and talk much more about the politics and economics.
Great. That would be fantastic, and that will really play along with the line we followed today, because Michael's talk was deep in terms of science, although he also outlined some solution. So next week, we're going to look at the policies and the economics. Thank you very much. I'm saying it again next week, but it's going to be the week after. Thank you very much, and see you after Thanksgiving for this class. Now, tomorrow we have another session that's going to be looking at the situation in Ukraine. It's titled ESG Concerns and the Reconstruction of Ukraine. So we have a scholar from Ukraine who is a visiting professor in the United States. So we look forward to your participation. Thank you and good night.
Thanks so much.